Hello everyone, welcome to my channel. Today I'm going to talk about the structural analysis of 2D truss structure by using object-oriented programming in Matlab code. And for this video, I'm going to use this example. So we have the 15 bar planar truss structure. We have a load applied to the node number 8 vertically. And if you're not familiar with the finite element method, you can check this book. It is a good book for doing the structural analysis. If you want to do the structural analysis by using the finite element method. Okay, so before we continue, please don't forget to subscribe and hit the notification button. And if you like this video, please put a thumb up as well. Okay, now we can start with the information of the truss structure. So I import some information here. So we have the Young modulus equal to 10,000, the material density equal to 0.1. We have the node coordinate, which taken from this picture. So we have the first node, second node until the last node, which is the node number 8. And next one we have the bar connectivity. So for the bar number 1, we connected from node number 1 to node number 2. So we import number 1 to node number 2 here, and we put in all the bars information until the last one, which is the bar 15 which connected from node number 7 to node number 4. So next we can start the new class. So I'm going to create a new class here. So a new class is created, and I will delete unnecessary information, and I'm going to change this class name and save it. So next we can import the class property, which is basically the truss property. So first it is the Young modulus, density, node, bar, section, load, support, and for the last part, the internal force, the reaction forces, and displacement. Next we can start the function of the class method. So I'm going to create the instance function. So we need the input information to the this class. So the first one is the Young modulus, and density, node coordinate, bar connectivity, and I will create the initial value. So the first one is Young modulus. It's equal to the information that we import here. So this will be Young modulus, and the property density is equal to density, and it's the same for the other property. And next I will create the initial information of the section, load, and support condition. So for the first one is section. So first I want all the section of the truss member equal to 1, and the size is length of the matrix bar, and this matrix only has one column. And next one is load. So initially all the loads are equal to 0, so this will be the matrix 0, and size of the matrix node. And next one is the support condition. So first this equal to 1, and I want the number 1 here represent the free degree of freedom. So next we can start a new object here. So we create a new object called Truss1 and call the class Truss. So the first import here is Young modulus, and the next one is material density that we put here. The next one is node and matrix bars. So first I will change the information here. So the first one is section, and then load and support condition. So for section and load and support condition. So first one I will call the property section and change all the section equal to 0.111, and for the load we call the property load and change following the picture. So the load is applied to the node number 8, and the direction is following the y-axis. So the value here will be 8 and 2. So 8 here is the node number and 2 represent the y-axis, and the value will be -10. Next we can change the support condition. So the initial value equal to 1. So I'm going to import some information here. 1 equal to free and 0 equal to fixed. So I'm going to call the support property and change following again from following this picture. So we have two support. The first one is located at the node number 1, and the other one is located at the node number 5. So we need two information here. So the first one is node number 1, and the second one is node number 5, and equal to 0 and 0. But we need to define the direction of the degree of freedom. So we have the pin support, so both degree both y and x and y axis are fixed. So we can input like this. So we already changed the support condition here. Now we can print the truss support condition. I'm going to run this. So we have the information here. So for the first node here, the value equal to 0. So 0 means fixed. And this is for the node number 5. So everything else are free. So the value is 1. And you can check the other information here, like load. So everything equal to 0, only the value here, which is at the node number 8, and y axis equal to -10. Now we need to start the structural analysis, so I'm going to create another function. We call this analysis. So first we can start with the node number equal to length, and we call the property node here, and the second one is the number of element. Again, it's equal to length of the truss property, and in this case we call the bar matrix. The other one is the number of degree of freedom, and it's equal to 2 multiply number of the nodes. So 2 here is for the 2D truss structure. And next we can find the length of each member, but first we need to find the differences of the node coordinate of each bar of the truss structure. So first we can call the information from the node matrix and do the subtraction. So the first one here is for the end point of each member, and the last information here is the start point of each bar. So in order to call the information or to know which node that each bar starts, and at which node we can call the information from the bar matrix here, which contain the connectivity of each bar. So we can call the bar matrix, and we want to do the subtraction for all member and for each node for both x and y axis. And I can copy this and paste it, but this is equal to 1 because this is the start point of each member. So once we know this, we can compute the length of each member, and we can call the command sqrt and summation. So the value 2 here represent the direction of the summation. So we want to do the summation horizontally, so we import the value 2. Now I can show you the information here, so let's run this file, but we need to call the function analysis. And we want to do the summation horizontally like this, so that's why this is equal to value 2. And next one, I want to show you the length of the bar as well. So this is the result. So next I will calculate the value c. So first we need the information from x2 minus x1, and then divide it by the length of each member. So we have the value d here as the x2 minus x1 and y2 minus y1, and we also have the length of the bar. So I will call this let's call this angle and equal to d divided by the length of each member. So this will equal to the value cx and cy as I show you here, and we can print this out. So this is the result. So we have cx and cy. Next we can form the transformation vector, which contain the negative value of cx and cy and the positive value of cx and cy. So we will call this A and call the command cat. So this is the command to combine the information of the matrix. It stands for the command concatenate. So first we need to import the direction. So I want to combine horizontally, so I put the value 2 here, and for the first matrix will be minus angle and then angle. So this is for the negative value and the positive value. Now we can run this. So this is the result. So now we have the transformation vector for each member. We can continue to form the stiffness matrix of each member. So first, the SS is the global stiffness of the truss structure. So it will equal to the matrix which has the size of the number of degree of freedom for the row and the same for the column. So this is the initial value. Now to form the stiffness matrix, we need to calculate the stiffness matrix for each member and then combine those information to the global stiffness, which is the matrix SS. So for k equal to 1 to number of element, and first we need to define the degree of freedom for each node. So I'm going to do some trick here, and I will show you later. So we call the degree of freedom index, and we equal to the combination of the information from the value AUX Okay, so I will show you the result here. So you can check from the first loop to the last loop here. So this is the value AUX, and you can confirm with this information. So the last bar is the bar 15, it starts from the node number 7 to the node number 4. So the degree of freedom will start from the degree of freedom 13, 14 to the last point here, the degree of freedom 7 and the degree of freedom 8. So the value here is important to form the degree of freedom here. So it's also the same for the other member. So this is the start point and this is the end point. So once you know the degree of freedom, you can form the stiffness matrix. So ES is the stiffness matrix for each member. But first I will compute the stiffness, which equal to Young modulus multiply object section. So we start from section number 1 to section 15, and I will use this information to compute the compute for the stiffness matrix for each member. So first we need to call the transformation vector. So again, if you don't know how to form the stiffness matrix for each member, you can read this book here. So the stiffness matrix equal to the transformation vector, the transpose of transformation vector, and multiply the value stiffness that I compute here, and then multiply the transformation vector again, but this time is not transpose, and we divide this value by the length of each member. So now we got the stiffness matrix for each member. We can form the global stiffness. So I'm going to call the stiffness global stiffness matrix here, and we need to import the degree of freedom information for each member and do the summation for each degree of freedom. So once you do the summation, you can get the global stiffness of the truss structure. Now next we can how we can define the free degree of freedom or the support degree of freedom. So first I will call this support reshape, and reshape the matrix support. So I will print this to show you what it looks like. So this is the support reshape vector that I created. So it contains all the support condition. So the first one is here is for node number 1. It's equal to 0 because it is fixed support. Now once we got all this information, we can find the index of free degree of freedom and also the support degree of freedom. So we call this free degree of freedom, and we can use the command find to find the index of the value which is not equal to 0. And I will copy this and change this to support degree of freedom. So in order to find the zero value in this matrix, you can put the sign here. Now I will run this to show you the result. So we have this index, and you can confirm with this feature. So we have the free degree of freedom that start from 3, 4, 5, 6, 7, 8, and then skip to 11 and 12, and so on. So the support degree of freedom is degree of freedom number 1, 2, 9, and 10. So now we have this information. We can start to form the stiffness matrix that contain only the support or the free degree of freedom. So first one, we call this KFF, and take the information from the global stiffness, but only from the row that represent the support, the free degree of freedom. So I will put the free degree of freedom information here. And for the next one is KFR. So the row is the free degree of freedom, and for the column we need to import the support degree of freedom information. And for the next one is KRF. It's equal to the transpose matrix of KFR. And for the last one is KRR. So this time is support degree of freedom for both column and a row of the matrix. So we have this matrix. We can compute for the displacement for each degree of freedom. So first we can define the load for the free degree of freedom. So we call this PF, and it's equal to I will reshape it first. So first the value from the matrix load, and this is the transpose. So we show you what this look like here. So this is the with the PF. Next, I will take only the value that apply, or the load value that apply to the free degree of freedom. So PF equal to PF and free degree of freedom. I can show you the result here. So this is the load that apply to all the free degree of freedom. Next, we can start solving for the displacement for at free degree of freedom. So we call this UF. It's equal to the result of the equation that we can solve from the matrix KFF and PF. So this here, it's something like load equal to stiffness multiply displacement. So this is the direct stiffness method that we use here, and you can check the book that I suggest earlier. So next I will define the displacement at the support degree of freedom. So we can use the command nnz. It's count the number of the non-zero value, and we can call the support matrix. But we want to find the zero value because zero means fixed. So I will put the sign here. I will show you the result. I think something wrong here. So I think this is not correct. We need to transpose this matrix from the row vector to the column vector in order to solve for this information. So we run this again. Right, so it is not error, so it means it's okay, and actually we can print the result here. So this is a displacement at each free degree of freedom, and this is the support, the displacement at support degree of freedom. Now I will combine these two vector to the vector u, but I will define the vector u here equal to the information from support matrix, and for the free degree of freedom it's equal to uf, and for the displacement at support degree of freedom it's equal to ur. And next we can reshape the u matrix u again, so it's equal to reshape u and 2. So 2 here define the side that you want to reshape, and I will show you the result. So I think we should transpose this matrix. So this is the displacement at each node. So this is the first node, the second node, and the first column represent the x-axis, and the the second column is represent the y-axis. So next we can take the information here to the displacement for each degree of freedom for each element. So I will call this u element and use the command concatenate again, and the direction is horizontally, so the value here too. And next we need to take the information from the matrix u, but we need to take also the information from the matrix bar, which contain the bar connectivity, and we define for all the value for all the bars. So I put the sign here and sign here represent for each for both axes y and z, and we need to combine with the displacement at the end point of each member. So I will copy this, paste it, but we need to change this to 2. So 2 represent the endpoint of each member. Actually, I will show you the result. So this is the result. So we have the start point of bar number 1, and this is the information for the displacement information for the endpoint of the first bar here. And there are 15 rows because we have 15 bar. Now we have this information. We can find the internal forces, which is the axial force. But I will need to we compute some information first. So Young modulus multiply section and divide by a length of each bar, and we use this information here to find the internal force. So I will call the property force that create here, and it's equal to the information that computed earlier, and multiply by the summation of A multiply U element, and this is the direction of the summation. So A here is the transformation vector that we define here, and this is for the placement of each element. So I will show you in this book the formula of the stress that we can use. So this is a transformation vector that we put here, which is the vector A, and the vector here is the U element. And if we multiply this by the area here, the result will be the axial force of each member. So this is the what I did here. Next we can define the reaction force. So it is equal to KFF that KRF that we define, and multiply UF plus KRO multiply UR, but we need to transpose this vector. So this is the reaction force. And next is the displacement. So actually we already defined the displacement here, so I just put U. So now we got the displacement, and next I will print the result, but we create another function in order to print the result. So first I will print the title. So let's call this internal force, and create a new line. Next I will display the result here. So all I need to do is just call the class property of force, and again we can do this for the reaction force and the displacement. So we call this reaction forces, and this is displacement, and also change the value here. Now we can run the function. So we call the function here and run it. So we have an error here, and I think I don't need to transpose this. So we run again. Actually, we have the result, but the information here is not shown. So it is because the class is by default is a value class in the Matlab. So in order to change the property of the class, sorry, the type of the class, we need to add a command here. So I will change the class here to a handle class and run this. So we have the information here. And actually we can reshape this matrix in order to make it easy to read. So we can reshape it. And transpose. Now we run this again. So now we have this reaction force matrix. So this is for the first reaction force at the first support, which located at the node number 1, and the other one is located node number 5. So we have the reaction force for the x-axis and for the y-axis, and this is the internal force for each member. And this, the last one here, is the placement. All right, now next all we need to do is to plot the structure. So we can create another function. I will call this graph, and the input will be the object and scale. So scale here is for the scale of the placement that we want to configure. So first I will create a new figure, and let's change the name here. Call this structure, and I will change the window state here in order to maximize the plot window. And we use the command hold on. Now we can plot the graph. So I will be start from 1 to the number of elements. So we use the command length of the matrix bar. So we start from 1 to 15, and first we can plot the undeformed shape. So we have xi, xf, and yi, yf, and this will be equal to node, and we take the information from the matrix with the matrix bar and start with I and 1, and this is 1. So the 1 here is for the start point, and 1 here is for the x-axis. So now we can copy and paste it, but we need to change this. So this is for the end point, so we need to change this to number 2 and keep this 1 because it is the x-axis, and change this to 2 and this to 2, which is for y-axis. Now we can plot it. So first is xi and xf. And next one is yi and yf, and we add some property here. And we can run it. Sorry, we need to call the graph function. So now this window pop up and you can see the graph here. This is the undeformed shape of the truss structure. So now we can do this for the deformed shape of the truss structure. So we call this deformed shape, but the coordinate here we need to modify with the displacement that we define. So I will call this UI, UF, and VI, VF, and this will be equal to xi plus scale multiply the value here. But we need to take the information from the matrix displacement. So we change this to displacement. Now we copy it and paste it here, here, and also here. And we need to change this HF, YI, and YF. And this is UI, UF, VI, and VF. And we change this to red, and let's add some star here. So we change the line width to, so we need to import the value here. Now let's say it's equal to 10 and run it. Now this pop up. So obviously the scale here is too much, so I will change this to, let's say, 1 and run it again. Now we have this result. So this is how you do the structural analysis by using the Matlab code, and we do this in object-oriented programming. So this is really a good way to do the structural analysis in order to control the information, and you can change the information later in order to apply to other example, or you can add some function to the program as well. So this is really a good way to do the structural analysis. So this is it for this video. I hope you guys enjoy it, and don't forget to subscribe and hit the notification button. And if you like this video, please put the thumb up as well. I'll see you guys in my next video. Thank you.